This is Unit 1. We're in Section D. And we now are going to turn to the idea that when we have these indeterminate forms, sometimes we need to combine some things that we already knew with some algebraic properties of limits. So what you have here first is a little chart that gives you these algebraic properties of limits. And I'd like to summarize them by saying it's okay to perform sort of typical algebra on limits. If you have the limit of the sum or difference of two functions, you can just split it up. You can evaluate the limit of the first and the limit of the second and add or subtract them. Here's one that we're going to see a lot this semester. If you have a constant multiple of a function, that constant multiple can in a sense be pulled out of the limit. You can just have the constant times the limit of the original function. We'll see the same three principles actually at work over and over again when we do not only limits, but eventually when we do derivatives and integrals. These next ones are more specific just to limits. They won't generalize as well to other things that we do this summer. So I'm going to kind of separate them right here. These will generalize very well, these won't. For limits, though, you can take the limit of a product by just multiplying the individual limits, and you can take the limit of a quotient simply by dividing the original limits, provided, of course, that the limit on the bottom isn't 0. We can never divide by 0. And finally, you can take the limit of a power of f by taking the limit first and then just raising it to a power. We're going to combine these 6 limit laws, what I usually call them, with some things that we already know about limits to calculate some new limits. In terms of things when I say what we already know, there are actually 3 special limits that I'll make use of extensively as we work with this. And these are limits that you have already investigated. This first one, the limit as x approaches 0 of sine x over x is equal to 1. We did that one numerically together. That was on page 7. We did this numerical limit and we allowed x to approach 0 from both the left and the right. And we discovered that the y values approached 1. So that one we did do. The other 2 listed here were also done numerically, but we didn't do them together. These 2 were actually part of your classwork number 2 assignment. But at this point, we're going to take them as givens and we're going to use them. Hopefully you came up with those answers on classwork 2. And if you haven't already, now you have a clue. All right, so I'll combine these 3 special limits with my limit laws up here to figure the rest of these examples out. First of all, I want the limit as x approaches 0 of 4 times 1 plus x to the 1 over x. You'll notice that other than the factor of 4, that's exactly the same as this limit over here. And one of my limit laws says it's okay to pull the constant multiplier out of the limit. So I could write that as 4 times the limit as x goes to 0 of 1 plus x to the 1 over x. This is now a perfect match for my special limit, which has the value of e. So I'm going to get 4 times e. I know that this function would have originally been undefined. I couldn't have put a 0 here because that would have made the denominator of that fractional exponent equal to 0. But there was a finite limit. So there's a hole in this graph at 0, 4e. All right, what about this next one? Again, it's quite similar to that limit whose value is e, but the numerator of the fraction is 3 instead of 1. That's really just the original raised to the 3rd power. And again, one of my limit laws says I can take the power and do it after the limit. So I'm going to rewrite this as the limit I know, all raised to the third power. Notice if I were to multiply those exponents, I would get the 3 over x right back again. What I have inside the brackets now is a perfect match for that special limit, so its value is e. And then I have to cube that, so I just get e cubed. Once again, the original didn't exist, so this graph is going to have a hole at the point 0, e cubed. And the value of the limit itself is e cubed. All right, take a look at this next one. The limit as x goes to 0 of sine x minus cosine x plus 1 over x. In this case, right now, I'm not seeing this as a perfect match for any of these, but I will notice that I've got the sine x over x, which I know, and then I've got, so what I'm going to try to do is split this up into 2 separate limits so that I can use both of these. So I'll start by saying, let's do the sine x over x, because that one I definitely know the result for. And then we'll separate the second one as the, and I could rewrite this, the order doesn't matter, right? I could write the 1 first and the minus cosine x second over x. And the sum of those is a common denominator. It would get me right back to here, so I haven't really changed anything. I've just separated my one fraction into 2 separate fractions with a common denominator. Now I've got the 2 limits that I know. This one's a perfect match for that, so its value is 1. And this one is a perfect match for that, so its value is 0. And therefore my result, 1 plus 0, is just 1. And this graph, again, doesn't have a y value, since x equals 0 in the denominator would have been a problem, but it does have a finite limit, so we have a hole at 0, 1. All right, let's look at this last one. This one, if you look at it, again, most closely resembles this. But I've got a little bit more of a problem this time. Instead of x inside the parentheses, there's a 7x. And I really don't have any algebraic way of dealing with that 7. I can't pull it out. There's no way to factor it out, right? I'm stuck with it. The saving grace is I also have a 7x here in the denominator. So what I'm going to notice is that both places that had an x in my original limit now have a 7x in my new limit. What I'm going to do here is make a substitution. I'm going to say, and a really common letter to use in substitutions in calculus is u. So I'm going to say, let's let u equal 7x. Now, since x is going to 0, that means u is also going to be going to 0, right? 7 times 0 is still 0, so that's good. My u value can be 0. And I'm just going to rewrite this limit. I'm now going to say, let's let u approach 0. And my limit is now 1 plus u to the 1 over u power. Other than the fact that I've used a different letter, which really doesn't matter, this limit is now an identical match for that one. And therefore its value is just e. It is really important, though, when you use these special limits, that you make sure you have exact matches. It would not be okay, for example, if this had just been a 1 plus 7x and this had been a 1 over 5x or something. I would not have been able to use this, These two variables are the same in the original, and therefore they have to be perfectly the same in the limit that I construct. So make sure you're getting perfect matches, either through the algebra like we did up here, or through a substitution like we did down here. All right, so this graph's going to have a hole at 0e. Speaking of those exact matches, let's take a look at a couple of other situations where we may need to do that. Here I've got 1 minus the cosine of x minus 2 over 3x minus 6. It's perhaps not a perfect match yet, and in fact maybe I should do something that I have kind of stopped doing for a little while. I didn't plug in when I was doing these problems over here. I didn't do the direct substitutions because all of these were such obvious variations on the three special limits. I just kind of jumped right to the solution. Let's go ahead and try that substitution on this one just to kind of show ourselves that, again, we're still really dealing with indeterminate forms. We just haven't talked about it for a little while. If I were to plug in the 2, I'd have 1 minus the cosine of 2 minus 2, which is 0. And 3 times 2 would be 6 minus 6. Cosine of 0 is 1. So 1 minus 1 is 0, and the denominator is also 0. And indeed, we do have an indeterminate form. So we need to do something. In this case, there is no obvious algebra for me to do other than perhaps factoring. Right? I could factor a 3 out of that denominator. Maybe we ought to try that. Now be careful here. Don't succumb to temptation. I would be remiss if I didn't remind you that you cannot cancel or divide out those x minus 2's. That x minus 2 is inside the cosine function. It's the argument of the cosine function. It's not available to do algebra with that denominator. So I'm stuck with this for the moment. Looking at that, the 3 in the denominator isn't really bothering me. That's just a constant multiplier of 3, or overall a constant multiplier of 1/3. And I could pull that out in front. Constant multipliers? Okay to bring those out in front of the limit. If that 3 is gone, because I pulled it out here, what I've got left is very, very similar to this limit. Right? The argument and the denominator were both x. They have to match. And they do now. The x minus 2 and the x minus 2 are the same. So I'm thinking this is going to be another one of those that I can probably do with a substitution. We'll use our favorite letter u again. And what if we let u equal x minus 2? Keep in mind, x was approaching 2. So 2 minus 2 is 0. That means u is going to approach 0, which is a very good thing, because this limit is only valid when 0 is being approached. So I think I'm ready to rewrite. I'll now say u is going to approach 0, and this becomes 1 minus the cosine of u. And remember that 3 is already out here, so the denominator is just the u. This is now looking really good. Again, this is a perfect match other than using u instead of x. It's a perfect match for this limit. The variables approaching 0, the argument and the denominator match. So I can say this limit is 0, meaning I've got 1/3 times 0, or 0 for my limit. The y value didn't exist, but the limit does. So we have a hole in the graph at 2, 0. Any of these, by the way, you could, of course, graph on a calculator and then just make the graph better by putting the hole in yourself. I'm just not taking the time to draw the graphs right now. All right, what about this next one? The limit as x approaches 0 of sine squared x over x. Once again, if I check, plugging in the 0, we should always try direct substitution first. Sine of 0 is 0. So I do have 0 over 0, our familiar indeterminate form again. So how am I going to handle this one? Well, as I look at my special limits, the one that it seems closest to, of course, is this one here, sine x over x. The problem is, in my problem, the sign on the top is squared. So what I'll do is I always want to separate out the part that I know what to do with. So I'm going to separate out sine x over x, because that's a limit we know. That's 1 as x goes to 0. And then the extra factor of sine x, I'm just going to write that as a separate fraction. I'll say times sine x, or sine x over 1, if you will. Notice that this is still sine squared x over 1x. So I haven't changed the value of my expression. It's still the same thing. I've just rewritten it in a different form. If I now take this limit, this first one, well, excuse me, let me separate these now. I know I'm allowed to separate into the product of the two limits. It's one of my limit laws. And this first one is a perfect match for one of our special limits. That one equals 1. This one, since my denominator can't be 0, it's specifically 1, right? I can just plug the 0 in. And since sine 0 is 0, I have 1 times 0 or 0 for the value of this limit. So this graph's going to have a hole at 0, 0. All right, I want to specifically compare these two examples, the one we just did and the next one. Notice they have a very different meaning. Here the sine function is squared, meaning it's sine x times sine x. Here it's only the argument, the x itself, that's being squared. So I cannot separate this into the product of two functions. That's not what it means. So I'll have to use a very different approach here. Let's just start by making sure we actually have a problem. If I plug in the 0, I'll have the sine of 0 squared over 0. That's the sine of 0 over 0. And sine 0 is 0. So there's that indeterminate form again. We do have a problem. All right, how are we going to handle this? Well, again, the same approach won't work. There's really almost nothing I can do about this. Typically, unless you start digging out a whole bunch of trig identities, which we'll do if we have to, but typically, unless you do that, there's not much you can do to change the argument of a trig function. It's better to try and leave the argument of the trig function alone and work with the other stuff in the problem, which is much more accessible. So in this case, if I say, this sure looks like I'd like to be able to make use of that limit, but I have to have the argument match the denominator. Algebraically, I could make that happen by multiplying by x. Now, of course, I can't just multiply by x in the denominator. I'll have to multiply by a form of 1, x over x, but that's doable. So let's work it that way. So there we go, multiply by the form of 1, x over x. And now I'm going to separate this out very strategically. I'm going to say, I'd really like these two x squareds together or excuse me, these two x's together to make an x squared, because that's going to be the match for my numerator. So I'd like this part all together. And then I'll use a limit law to just write times the limit of the x separately. So there we go, everything's there. Part I circled in this limit, and then times that extra x over here, still having the limit as x goes to 0. All right, we're almost there. This first part is almost a perfect match, but of course what I really had here were x's and not x squareds. So once again, I can handle that with a little substitution. I could say, let's let u equal x squared. Since x is approaching 0, 0 squared is still 0. So I would have the limit as u approaches 0 now, and that will become sine u over u, which is exactly what I want. Other than the fact that I've used a different letter, that's a perfect match for this limit. So that's just going to be 1, no problem. And then I still have this other one, the limit as x goes to 0 of x. Again, not worried about that. Plugging x in there is going to be easy. So I get 1 here, times 0 there, and 1 times 0 gives me 0. So my limit is 0, and once again I have a hole at 0, 0. What I'd like to particularly point out to you here is that even though I got the same answer for these two examples, the thought process in terms of why the limit turned out to be 0 was very different in these two problems. You've heard this in math a lot, but it's even more true now that you're in calculus. The process is far more important than the final answer to a mathematician. And so when you do write out these limits, it's going to be very important to me to be able to follow your work and to understand your precise mathematical process. So be sure you show those really, really clearly when you do work to hand in to me. All right, this is getting a little lengthy and we still have a little ways to go, so I think we're going to pause and make one last video for this section.